Now, so far we've used truth tables to determine the truth conditions for a compound proposition. We've also used truth tables in order to determine logical properties of individual propositions as well as logical relations between compound propositions. Today we're going to look at how we can use truth tables in order to determine whether or not a deductive argument is valid or invalid. As far as this goes, we've used a method for determining validity in the past, which is the method of counterexamples. For instance, you might recall the example I used in the past, which was if you are getting an A, then you will pass this class. You will pass this class, therefore you will get an A. And in order to determine whether or not this is valid, what you do is you try to imagine an example in which the premises are true and the conclusion is false. Now this is easy in some cases. For instance, right here, this argument actually follows that pattern I just mentioned, which would be if P then Q, Q therefore P. And we can imagine a scenario in which this would be true, where if we assume P is you are getting an A and Q is you will pass the class, and we can assume, well, you will pass the class, therefore you'll get an A. We got to say, well, what if you're getting a B? In that case, then premise 2 would be true, and yet the conclusion wouldn't be guaranteed by the truth of the premises. And that's an instance where the argument is invalid. And when we're looking for an invalid argument, what we're always trying to do is look for a scenario in which the premises are true, and I'm going to write this right here for you to see, and yet the conclusion is possibly false. And the word possibly needs to be here. So I can't write this very easily. Possibly false. It doesn't actually have to be false, but the idea behind invalidity, that's an arrow, by the way, if you're wondering. The idea, I just made it worse. All right, forget that. That's an arrow. So the idea behind invalidity is that we assume that the premises are true, and then if we can imagine a way in which the premises are possibly false, then the argument is invalid. So what we look for, in other words, is TT or true, true, false. That's the way we should think of invalidity. And if we can't imagine a scenario, then the argument is valid. Now, it's fairly easy to do when we're dealing with simple syllogisms like this. In fact, as you should hopefully remember, this right here is a very well-known fallacy, the fallacy of affirming the consequent. We learned this. But what do we do when we have more complex arguments like the one right here? What do we do with this? It becomes extremely hard to determine whether or not this is valid or invalid just using our intuitions. I mean, I personally can't look at this and just say, yep, that argument looks invalid to me. Maybe you can, and if you can, good for you. I'm sure I could construct an argument that's even more complicated than this, in which you wouldn't be able to do that. And in some scenarios, it's not really even easy to come up with, when we have content to the propositions, it's not always easy to imagine a counterexample just because there's so many parts to the argument. And for these arguments, what we're going to do is we're going to construct truth tables in order to prove validity or invalidity. And as far as this goes, there are going to be 3 steps that we have to follow in order to construct the truth table for validity and invalidity. And the very first step is that we construct the truth table. And by this, what I mean, and I have it filled in here, is we're going to put the premises and conclusion on the top line of the truth table, and then we're going to put all of the premises, premise 1, 2, and then we're going to separate the premises and conclusion by using a /. You'll see what I'm talking about in a second from now, but basically we'll have premise 1, we'll have columns for it and columns for its connectives. We'll put premise 2, we'll just put a space in between 1 and 2, and then we'll put a / and we'll put the conclusion after it. So once we've constructed our truth table, kind of laid out the template for it, then we're going to just complete the truth table the way we have done in the past. We'll fill in the truth values for all the atomic propositions in premise 1. We'll fill in the truth value for the connective, and then we'll fill in the truth value for premise 2, fill in if there are any connectives, fill that in, and then we'll fill in the truth values for the conclusion as well. And then once we have done that, then we move on to step 3. And in step 3, this is the only part that's really going to be completely new. But what we're going to be looking for is we're actually going to be looking to prove invalidity. we're going to be looking to prove invalidity. And if the argument is invalid, just in case, on one of the rows, and it only has to be on one. If we can find one row in which we have a true premises, both premises are true, and one row that also on the same row, it can't be, row number 1 has true premises and there's a false conclusion on row 2. But if we can find one row that has true, true, false, then that argument is invalid. And if we can't find a single row that has true, true, false, then the argument is valid, because we only have two options, either valid or invalid. If it's not invalid, then it just follows from just sheer reason alone that it would be valid. So that's what we're going to be looking for. Now, all this might be a little confusing, so let's do a couple of examples. In fact, this is all we're going to do today, is just look at different examples. Now, this is an argument you guys are familiar with. You already should know this is a fallacy here, the fallacy of affirming the consequent. I just had this a second ago, but here's how we're going to use the truth tables to test validity. The very first thing is we're going to construct our truth table. That's step 1. And here's what it's going to look like. And you can see right here we have our columns for our different atomic propositions. We only have 2. We have P and Q. We just repeat those down here. Then we have premise 1, which we write right here. And I have more spaces than are needed. You don't have to necessarily have space here, but you do need to indicate in some way that there is a gap between these. Like some people on their truth tables, they'll just draw a line right here, and that's fine. You just need to indicate that there's a gap in between the first premise. But here's the second premise, right? Premise 2, you can see that. Here, I'll put a 1 up here for you so you can see this is 1, this is 2. And then we have this forward slash, and the forward slash represents what comes after it. This is our conclusion right here. All right? And so we've constructed our truth table. We have P's and Q right here. These two columns are just to keep things straight. And just like any truth table we construct that only has 2 atomic propositions, we're going to have 4 rows. Then we have a column for, you look right here at premise 1, we have a column for the first atomic proposition, a column for the connective, a column for the second atomic proposition. We come over to premise 2, we have a column for, well, the only thing that's in that is just the atomic proposition. We have a forward slash, and then we have our conclusion right here. Then step number 2, we come to that. We complete our truth table. And here we just do exactly what we've done in the past. First thing is we're going to lay out our truth values for our atomic propositions, and true, true, false, false, true, false, true, false. And then we transfer these everywhere we see the atomic proposition, just as we've done before. And then this one is a pretty simple argument. We only have one connective that we're going to have to figure out, and here is that connective right here. So what we're going to do is we're going to come right here and write in our truth value. So whenever we're dealing with a conditional, the only time it's false is when the antecedent is true and the consequent is false. This is the only time it's false, and in all other occasions it's going to be true. So that's pretty simple. Now we have that done, and let's see if we can go to the next slide. We're going to determine validity. And what we're going to be looking for here is we're going to be looking for, we have 4 rows, 1, 2, 3, 4. And we just have to find one. If we can find one in which this premise is true, this premise is true. Here, let me write this up here more clearly. And then this is false. If we can find one, that looks like a K, sorry. False, then it's invalid. So we're going to be looking at this column here, because that's the truth of premise 1. This column here, because that's the truth of premise 2. And then this column here, because that is telling us the truth of the conclusion. So let's do that. We'll start with premise 1. And you see right here, true, true, true. So that doesn't help us out. Then we come right here. False, false, true. That doesn't help us out because, again, we're looking for true, true, false. In fact, I should go ahead and tell you this. Whenever you have a row in which one premise is false, you can immediately just ignore that, because the only thing that what you're looking for is true, true, false, because that would be a case of an invalid argument. That would be where the premises are true and the conclusion is false. So anytime you come across a row in which one of the premises is false, that's not going to help you. All right. then we come to this one. True, true, false. Oh, bada bing, bada bang. And here we have what we're looking for. This proves to us why this argument is invalid. It shows us the condition under which this argument will not work. Remember, if an argument form is valid, then that form always must work, right? And what it means when I say it works is just that if the premises are true, then the conclusion must be true. You see right here, it works for this. When P and Q are true, then yeah, the argument's going to work. But if P is false and Q is true, then we have true, true, false. And so the argument form doesn't work for us. If it's valid, it's always valid. And that's not what's going on here. So road 3 proves that this argument is invalid. Now we don't need to look because we've already proven this argument is invalid. Road 3 proves it. But just to kind of cross all our T's and dot all our I's, we'll look down to row 4, and that one doesn't help us out. The one that shows us this argument is invalid is row 3. So that's how we do it. Well, what we're going to do is we're just going to do a couple more examples of these today, and then I'm going to turn you loose on your homework because different examples reveal different things. But let's look at example number 2. If P then Q, not P, therefore not Q. Okay, well, hopefully you know that this is also an invalid argument. You should remember this is an instance of what we call denying the antecedent. But let's prove this argument is invalid using our 3-step method. So step 1, we construct our truth table. And just like before, what we're going to do is we're going to write out our argument on a single line. We have premise 1 right here, if P then Q. Premise 2 right here. And let me put some brackets around this so you can see. This is 1, this is premise 1, and this whole thing is premise 2. And then we have our forward slash to represent that this right here is our conclusion. So we've constructed our truth table. Then we come to step number 2, which is that we complete the truth table. And what we do here is we just fill in the truth values just like we've done in the past. So I'm going to go ahead and put in the truth values for all of our atomic propositions. Then what we do is we're going to fill in the truth values for the connectives. And so we're going to do that kind of the same way we've done so far. So we'll begin with premise 1. Again, logically speaking, we could fill in the truth values for these connectives in any order we want, but we'll just start right here. And the truth value for this connective is just the same as a conditional, so it's going to be true. Remember, it's only false if the antecedent is true and the consequent is false, and then true. So we've done that, and then we'll come to premise 2. If the computer will obey my authority. All right, and this is true, so we put a false here. True, we put a false here. False, we put a true here, because remember we're just doing the opposite. That's what we do with negation. And then we come finally here, and we just do the opposite. That's false. So that's false, so that would be true. That would be false, and this would be true. Okay, so now that we've done that, we come to step 3 and we determine validity. And what we're doing is we're just looking for one row in which the premises are true and the conclusion is false. Now, we're going to use this column right here because the conditional represents the truth value of this premise. We're going to use the negation right here because that tells us the truth value of this compound proposition. And then we're going to use the negation right here, that column, because that tells us the truth value of this entire compound proposition. So let's begin. And you see right here, true, false. As I said, as soon as you come across a premise that's false, you can just skip to the next line or the next row because we're looking for true, true, false. Don't have that here. False, false, true. That doesn't help us. True, true, false. Now this is just a coincidence that row 3 proves validity here. Don't think row 3 always proves invalidity. Just happened in these two examples to work out that way. But here we have the instance where we've proven this argument is invalid. And we've done that because we have this premise is true, this one is true, and yet the conclusion is false. Again, we don't need to look at the conclusion, and as it turns out, I'm sorry, not the conclusion, but the final row, row 4. As it turns out, this doesn't help us here, but we've proven this argument is invalid. True premises and a false conclusion. Well, let's move on and do another example. And here we have a case of modus ponens. And so you know that this is valid, but we're going to prove that. Step 1, construct our truth table. Here it is, just like the previous examples. Step 2, we fill in the truth values or complete it. Now, I just went ahead and took the liberty to do that because this one's pretty easy. And then what we do is we come to step 3 and we determine validity. And we have here all of our values. And I've already gone ahead and I've marked them for us. But what we're looking for is a row in which we have true, true, false. Now, let's begin row 1. True, true, true. Okay, that's okay. False. Well, we don't have true, true, false. Here we have false and false. So we only have one row, which is row number 1, in which both premises are true. In all the other occasions, the premises, at least one premise is false. And this is the only one in which both premises are true. And as it turns out, the conclusion is also true. So we don't have a case in which we have true premises and a false conclusion, and for that reason, this argument is valid. We're unable to prove invalidity, and if we can't prove that it's invalid, the only remaining option would be that it is, in fact, valid. All right, well, let's do a slightly more complicated one. So here's an argument. If P or Q, then R. P and Q, therefore R. Now, this one, we don't have a name for it, whether or not it's a fallacy or it's a valid form of argumentation. It's not, modus ponens, nor is it an instance of, like, for instance, affirming the consequent or denying the antecedent. It's not modus tollens. It's not one of the standard forms of deductive propositional arguments. And it's not easy to look at this and just say, yeah, this is valid, or yeah, it's invalid. And so what we're going to need to do is construct a truth table in order to determine validity. Now, like with all truth tables, the very first step is we have to calculate the number of rows we're going to need. So we raise 2 to the power of the distinct atomic propositions. And here we have 1, 2, 3, P, Q, and R. So we're going to raise it to the power of 8. I'm sorry, to the power of 3 and come up with 8 rows. I don't have space on this slide to put a truth table this large, so we're going to have to change screens. And here is what it's going to look like. We have our columns for P, Q, and R right here, just so we can keep these values straight. And then notice right here that this entire proposition, this is premise 1. P and Q, this is premise 2. We have our forward slash to represent our distinction for our conclusion, and R is our conclusion. And then what we're going to do is we're going to fill in the truth values for all these atomic propositions. And we would start right here. I'm going to kind of rush through this, but we have 8 rows, so you know that the first column is going to be 4 truths and then 4 false. Then we're going to come here and do half of 4, which is 2 true and 2 false, 2 true and 2 false, and then half of 2, which would be 1 true, 1 false, all the way down. And then we just fill in those values everywhere. So this is what it's going to look like. And then once we get all these filled in, what we do next is we come in and we fill in the truth values for all the connectives. Now, I already have it highlighted here for you to see, but you can see that we need to fill in the truth values for the connectives in the first atomic proposition. So our first compound proposition, or our first premise. So here is, I'll just circle it, our entire first premise right here. If P or Q, then R. And we have 2 connectives. We have the or, and then we have the conditional. And the conditional is our main connective. We always start with the connective of least scope. And a disjunction is true just as long as one of the 2 disjuncts is true. And all the way down, we can see that at least one of the 2 disjuncts is true until we get to the final 2. These are going to be the only instances where Oh, sorry. I paused for a second because my eyes got offline. These are going to be the only instances where this disjunction is true. In all the other cases, it's going to, false. All the other cases, it's going to be true. Now, we skip ahead and we'll do the second connective here. We'll do the main connective for our premise 1. And we'll use these values here, the values for R and the values for the disjunction. And we can go ahead and fill those in. And just so you can know, I'll kind of skip through that. The only cases where it's going to be false are right here, because we have a true antecedent and a false consequent. Right here, again, true antecedent and false consequent. And here, we have a true antecedent and a false consequent. And in all the other cases, it'll end up being true. So we have already identified the truth values for this first proposition here. I'm going to leave this highlighted just because if I didn't, it's hard to kind of keep your eyes straight. But this highlighted region right here indicates that this column is the one we're going to be looking at. Then we're going to come over here and we're going to look at premise number 2. And we've already filled in our truth values for our atomic propositions, so we just determine the truth values for our connective here. And the only time a conjunction is true is when both of the conjuncts are true. And that's only going to be in these first 2 rows. So we can fill that in, go ahead and fill that in. And now we have completed our truth table, and so we come to step 3, determining validity. And what we're going to be looking for is an instance of if one exists, and maybe one doesn't, where we have premise 1 is true, premise 2 is true, and then the conclusion is false. So just to save time, I'll go ahead and color this in for you. And you can see right here, now by the way, when you're doing your truth tables, you don't have to color these in, you don't have to have highlighters and stuff. I'm just doing that for you guys to see. But you can see right here that in row 1, we have true, true, and true, but everything else, row 2 through 8, we have no instance where we have 2 true premises and a false conclusion. In fact, we have no instance beyond the first row where we have even 2 true premises. And as I was saying, if you see one false premise, you can go ahead and discount that row because that's not going to tell us true, true, false. Right? It's just not by definition telling us that. So this argument actually is valid. This is a valid argument. Again, you might not have thought that from just looking at it because, you can go back a couple slides if we can. The computer will work with us. Yeah. Can you look at this and just say, oh yeah, that's valid? I certainly can't. I wouldn't have known if it's valid or invalid or what just from looking at it. But we can construct our truth table and fill in all the steps, just do all 3 steps as I just said, and we just can't find a case where we have true premises and a false conclusion. And for that reason, it is valid. Now here we come to our final argument that we're going to do today, and then I'll go ahead and share with you your homework assignment. But here it is. This is similar to the last one, but we have P or Q, or if P or Q, then R, not R, therefore not P and Q. Now, this is one certainly has a lot going on here, and I can't determine if it's valid or invalid. So we begin just the same way with constructing our truth table. And exactly like the previous example, we're going to have 8 rows. So I'll just go ahead and put that up here. And then we fill in our truth values for all of our atomic propositions. Now we have a lot going on here, but something, and I might have gone a little too fast, is that we have our first premise is right here. This is premise 1. Our second premise is right here, premise 2. And then this is our third premise right here. And the chart for this premise right here is going to be identical to the chart on the previous example. So I'll just go ahead and fill that in. And then for not R, well, you can see right here, we just fill in opposite values for everything under R right here. And then for not P and Q, we determine the truth values for the conjunction here and then just do the exact opposite right here. So we have this done, and then we'll come to step 3 and we'll determine validity. And what we're looking for is any instance where we have a row in which the premises are true and the conclusion is false. So do we have that? True, false, no, false, true, no, true, false, 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 false. We only have one row, which is the last one. This is the only row in which we have 2 true premises, all right? True and true. But look, our conclusion right here is also true. So we don't have a case where we have true premises and a false conclusion. And so for that reason, this argument is also a valid argument. This is a valid argument. And again, just from looking at this, I certainly couldn't tell. I don't know if you could or not, but we're able to use this truth table test in order to determine validity. Now, if this wasn't abundantly clear from the very beginning, what we're always doing when we do these truth tables is we basically put all three propositions, or just to review, we put all three, or the two premises, premise 1 here, premise 2 here, and then the conclusion here. Then we determine the truth values of the main connectives for each proposition, or the premise and the conclusion, and then we just look at the truth values of the main connectives and we say, do we have true, true, false? If we have one row in which we have true, true, false, then the argument is invalid. If we have no rows in which we have true, true, false, the argument is invalid. Well, the good news is if you guys are having so much fun with this, I'm sure you're going to have more practice at this. So I have a couple of problems. I don't have too many for you. You have right here, you have what, 5 problems for homework. I tried to limit it a little bit because it is the end of the semester, and also drawing up these truth tables is a real pain in the neck. But this is your homework, and for these problems, you're just going to be constructing truth tables in order to prove validity or invalidity. If you have any questions about this, please feel free to email me.